Astronomers have used a new camera called the Hypercam to analyse a type of small, dim star that has proved elusive to standard cameras. The new camera has allowed them to make detailed measurements of this cool subdwarf star 1500 light years away, and it's the first time they've been able to confirm the predicted model of this type of star. I'm Ruby Osborne, and I spoke to Dr. Stephen Parsons from the University of Sheffield about what makes this star so interesting and how the Hypercam has helped them to study it.
So we were looking at a type of star called a subdwarf star. So this is a type of star that is fainter than a normal star, and we believe that's because it has very few metals in its atmosphere. That implies it's a very old star. It's part of a binary system. By that I mean there's two stars orbiting each other. They actually orbit each other in about 2.5 hours. And the other star is actually a dead star. It's a type of object known as a white dwarf. And the nice thing here is that the orbit of these two stars is aligned so that we actually see them passing in front of each other here at Earth. So we call it an eclipsing binary. And the power of eclipses is that it tells you exactly how big the stars are. You can use it as a kind of a laser going across the star, telling you exactly how big it is.
What is so special about this particular camera that you were using?
Most cameras in astronomy are very slow. So you take a picture and it takes maybe a minute or so. But the camera we were using can actually take 1,000 pictures per second. We can look at this eclipse in far more detail than you ever could with another slower camera. Because it's such a short period, only 2.5 hours, everything is happening really fast. And white dwarfs are very small, about the size of the Earth. As they pass behind the star, it's only about a minute or so before the star totally disappears. And then a few minutes later, it will reappear. And so everything happens really, really rapidly. And so you need a camera that is able to take pictures very, very quickly.
How come this camera can take those photos so fast? How can it get enough light in to take a picture if it's only got that little time to do it?
One of the main things is it is attached to the largest optical telescope in the world, the GTC on La Palma. It's got a huge 10-meter mirror, and so it gathers a lot of light. And then we can do very clever things with the electronics to try and go as fast as we can as well with the camera.
And are these pictures in black and white, or are they in colour?
So we look at visible light, the same light that we see with our eyes, but we split it up into 5 different colours. There's actually 5 cameras combined, a blue, green, yellow, orange and red camera. And that actually tells us a lot of different information. Things that are different temperatures, then they have different contributions of light in different colours. And so actually if you split up these images into different colours, you get all this extra information for free.
So what have you learnt from looking at this star?
Well, so the idea of these lower metallicity objects is that they should actually be smaller than a normal star. From our eclipse measurements with the camera, we were able to tell that this star is indeed quite a bit smaller than it should be for a normal star of its mass, which is exactly actually what the theory predicted it should be. But this is the first time we've actually been able to tell that for sure.
This particular star that you were looking at, you said it's very old. Do we know how old?
Well, one of the nice things about the white dwarf next to it is they don't actually produce any of their own heat anymore. Like I said, they're dead stars, and so they just cool forever. If you know the temperature of the white dwarf, which as I said we can get from the colours, then we know how long it's been cooling for, and then you can kind of make some assumptions on what kind of star it came from. The conclusion is that it's probably at least 10 billion years old, but may well be quite a bit older than that.
And stars, they're very pretty in the sky, but they're a very long way away. Why should we spend all this time studying them?
This particular object, I think it has quite a useful way of explaining maybe how alone we are, or maybe how many other aliens there are out there, perhaps. Hydrogen and helium were made shortly after the Big Bang, but basically every other element was then made in stars. So the first generation of stars that existed were essentially pure balls of hydrogen and helium. Each subsequent generation of star has a little bit more metal in it. There were no rocks around those first generation of stars. There was no planets or anything. And the question is, was there enough metals made in that first generation of stars so that that next generation could form planets? On the other hand, maybe you needed 2, 3, 4, 5 generations of stars to kind of build up enough material to actually be able to create planets and sustain life. Maybe on the one extreme, maybe we're the first life to emerge in the galaxy. On the other hand, maybe it's been around for billions of years all over the place. With studies like this, looking at these kind of stars, you can start to piece this kind of thing together and say, where did life come from?
Do you think we're close to an answer on that?
I think this was maybe one step on the ladder to getting there. There are a lot of missions coming up in the next few years that may actually be able to directly find signatures of life on other planets. That would maybe tell us where we are now, but it doesn't tell us where we were billions of years ago.
That was Dr. Stephen Parsons from the University of Sheffield, and that study was published recently in Nature Astronomy.